Hello, welcome to our presentation on quantum computing. My name is Peter Lee, and I major in computer science.
My name is Archer Sagaskie, and I major in physics.
So, what is quantum computing? Well, currently, mainstream computing has limitations. So, right now, in your traditional computer, we are limited to just computing processes one at a time. So, essentially, we're stuck with our traditional calculations, and this limits our potential.
And quantum computing is far superior in comparison to current technologies. The implementation of quantum computing could both do good things and bad things for the future.
So, what is quantum computing in detail? In the computing field, there are three main points when it comes to quantum computing: binary versus qubit, superconductors, and decoherence. Binary versus qubit is a concept where in traditional computing, you would have your ones and zeros. So think of it like a light switch where your zero is off and your one is on. This would lead to just your traditional one processee at a time, since you're stuck with your ones and zeros. Whereas in qubit, in quantum computing, qubit is a new method where essentially the light switch is stuck in the middle. So it can act as a zero, but it can also act as a one at the same time. This may sound good, but it can lead to a lot of stress on the processor, which goes into superconductors. Superconductors are a new material where essentially we're able to do quantum computing with lower temperatures and also decent performance. However, this can lead to complications such as material development as well as just engineering the thing in general. But one main con is decoherence. Decoherence is essentially whether you have a physical interference or a radio wave. And those two things can actually screw up a quantum computer and it could lead it to calculate incorrect things. And now onto our physics portion.
Now, I'm going to briefly talk about three main things with physics in quantum computing. The first being quantum mechanics. This describes the behavior of matter and energy at a subatomic scale. Quantum physics challenges classical ideas about how the world works and has led to the development of technologies such as superconductors and quantum computing. A great example of superposition is flipping a coin in the air. The possible outcome could be heads or tails, but in the air, it's undecided. And the coin is then in a state of superposition. The superposition of qubits allows them to process millions of operations simultaneously. Now, quantum entanglement happens when two systems are linked so closely together or so closely that knowledge about one gives you immediate knowledge about the other, no matter how far apart they are. This allows quantum computers to solve complex problems even faster.
And now here's a quick demo. On the left, you see a classical bit. On the right, you have a qubit. Essentially, this is one of the most basic ways to describe quantum computing. So you can see on the left side, it takes longer for a traditional computer to solve the maze, whereas a quantum computer, it's able to solve the maze in just a few seconds due to the concept of the qubit itself. So while you see the qubit solve the maze already, the classical bit is still solving, and then it solves it right now.
So, why is quantum computing important, right? Utilizing quantum physics and qubits allows for computations to be done significantly faster than current technology.
And this enables a lot of advances in several fields of science and industry. So you can see scientists modeling cancer cells right now. In traditional computing, it'll take you months just to model one cell, whereas with a quantum computer, it's able to model that one cell in just a few hours.
And it is also capable of breaking current methods of encryption and creating new methods of encryption. One example of this is Shor's algorithm. This can break RSA encryption really quick because Shor's algorithm can factor large numbers exponentially faster than classical computers can. It does this by using properties of quantum superposition and entanglement to perform efficient factorization.
So, this can lead to a lot of threats in our current industry because quantum computers are able to break a lot of traditional encryption methods we're using. Hence why we have these quantum resistant algorithms. So now, if you look at the top two, these are your crystal kyber and crystal dilithium. Essentially, these two encryption algorithms operate on the same principle, security via complexity. So what do I mean when I say security via complexity? So, in your traditional encryption algorithm we've been working on, it's essentially an 8-bit format, where essentially we're trying to factor in our ASCII characters through the 8-bit encryption alphabet. But in these encryption algorithms, they're using 256. 256 is essentially 10 times harder than what we're working with right now. So they're trying to outpace the quantum computer or try to drain its resources from being able to solve the encryption method. If that doesn't work, we have Falcon. Falcon is essentially taking it one step above Crystal Kyber and Crystal Dilithium. In fact, it goes up to 512-bit, which is essentially double of what we're working with right now. And in the current development and field of Falcon, they're trying to reach infinite complexity where the algorithm is so long, no computer is going to be able to solve it without the key. However, that portion is at risk as well. Hence, we have Sphinx Plus. For Sphinx, it's essentially trying to change the digital signature. So for every message we send, we have a digital signature. But in Sphinx, the digital signature changes from sending, from reading, from receiving. So it keeps changing the digital signature all the time so that even if a quantum computer solves one signature, but then the other person sends another message, well, that solution is useless now because it changes the digital signature every time.
So, what are the cons of quantum computing? First one is that it's expensive. It's expensive because of the research and development costs, as well as maintaining a constantly cool temperature using cryogenic cooling systems. Hardware challenges are also associated with this because quantum computers are specialized. They use specialized hardware that uses superconductors, and we don't have a perfect superconductor. Also, designing a computer that can withstand this high temperature produced is a huge challenge. And also, error rates and decoherence. Qubits are susceptible to environmental errors due to decoherence and noise. Environmental factors like background radiation can cause a quantum state of qubits to collapse. This can produce incorrect outputs when trying to solve a problem, which reduces consistency of problem solving.
And now onto our conclusion. After researching quantum computing, we have came up with four main points. The first point is that quantum is changing hardware and software. With the development of superconductors, we now need new hardware to support that so that we're able to do quantum computing in the first place. Also, software is changing because with the concept of qubits, we now have to do programming in a wholly new way to factor that in, since we're able to have bits being able to coincide with each other all the time. Point number two, quantum computing is essential to encryption. While yes, quantum computing is destroying our current encryption algorithms, we're able to use that same quantum computer to make new encryption algorithms so that we can stay secure in the end. So it ends up being a double-edged sword.
And the third point is that we can utilize complicated problems in physics to create better encryption algorithms that classical computers are not capable of solving. So, kind of backing off the second point, because we're using qubits, this utilizes quantum mechanics, and using that, classical computers do not, which then makes it capable of encrypting better methods using quantum mechanics and quantum computers. And the fourth point is it meshes the fields of physics and computer science to further develop each respective field, which advances all fields.
And
And
that's,
that's our presentation.
yep, thank you for listening.